Hello everyone, welcome to this lecture on Fourier transforms. Today we are going to talk about Fourier transforms, and earlier we have already done Fourier series, and these two are very closely related to each other. Okay, so before we actually give the mathematical definition of what Fourier transform is, let us see uh, from the Fourier series point of view how much they are related, how you can visualize it. Okay, so for that let us consider a periodic function, periodic pulse, okay, given by this function, and you can see that the pulse is from -1 to 1. So from this point up to here 0, then takes value 1, then takes value 0 up to 1. Okay, and then this pulse is again repeating, okay, on both sides. So this is a periodic function, and we have already done in previous lecture that we can calculate the Fourier series for such functions which are periodic in the time domain, and we can draw and find the Fourier series. That means we can find the function in terms of the trigonometric functions sine and cosine. So we can find an infinite sum of in terms of sine and cosine. Okay, and you can see that when the number of terms on the right hand side increases, then the function actually converges back to this uh, pulse function. Okay, so this is a Fourier series. Okay, and but what if this function consists of a single pulse instead of a periodic pulse? Okay, so instead of periodic pulse like this, if we have only a single pulse, okay, and the function say is 0 from minus infinity to uh, up to this point minus half, and for t minus half to half it is 1. So there is a single pulse generated, and after t is equal to half the value is again 0. Okay, so the function is not periodic and it is defined from minus infinity to infinity, so we cannot just make it periodic. Here the function is defined only from -1 to 1, so we can assume that outside this the function is repeating and we can say that it is periodic. But in this case the function is defined from minus infinity to infinity and only a single pulse is generated. So in this case we cannot calculate this Fourier series, but what we do is we calculate the Fourier transform of this function, which represent this single pulse or any function which is defined from minus infinity to infinity. And if you calculate the Fourier transform of this function, then the Fourier transform of this function is this fs is equal to 2 by s sine of s by 2. Okay, so this is the figure for this Fourier transform of this single pulse function. Okay, so you have a time domain function and you convert it into a frequency domain function using the Fourier transform. Now as I said that the Fourier series and Fourier transform, they are very closely related. Okay, so if you just look at the coefficients of cosine, which is the secants, here it is 2 by n pi sine of n pi by 2. Okay, so if you look at these cns and if you compare with this Fourier transform, then you can see there is some relation. Okay, here it is 2 by s sine of s by 2, similar to this cns are 2 by n pi sine of n pi by 2. Okay, so the coefficient cns are related to this Fourier transform function. Okay, so this is one point of view. The second thing I would like to place is that let us again see the single pulse for a time minus half to half, say, and what if we increase the time of this pulse? Okay, so if I increase the time of this pulse, say the time is -1 to 1. Okay, so the width of the pulse is increased, and say it is further increased to -2 to 2. So what happens if the time of a single pulse is increased? What happens to the corresponding Fourier transform function? Okay, so that's what I want to see before I give the mathematical equation. So let us see what is the Fourier transform of this first function, this second function, and this third function, where they are single pulses but with the the width of or the time of the pulse is increased. Okay, so if we calculate the Fourier transform of this function, which we plotted on the previous page also, then this is the frequency, this is the Fourier transform of this function ft. Okay, so if in the time domain the width of the pulse is increased, what happens in the frequency domain to this function? Okay, so you see that the transformed function also varies when the function width is increased. Okay, so and it varies both in amplitude as well as in width. Okay, and we if you see the plot of this third function, the Fourier transform is of this function where time is -2 to 2 for this pulse, then you see that again the amplitude is increased from 2 to 4, and the width of the function becomes narrow than the previous one. Okay, so when the pulse becomes wider and wider, the corresponding Fourier transform becomes narrow and narrower. Okay, so that's one result from here that I wish to show. Okay, now we can define this mathematically, that if we are given this function in the time domain, then how we can find the function of this in the frequency domain. Okay, so we define the Fourier transform mathematically now, that the Fourier transform of the function xt is defined by the Fourier transform of xt is an integral minus infinity to infinity of the function xt times exponential e power minus iota st dt. Okay, and then the Fourier transform we represent as x of s. Okay, so if you integrate this with t, then we substitute the limits of t, then it will be a function of s. Okay, so we can write it as some function of s, which we are denoting by capital X of s. Okay, and also we can find the inverse transform. That means if you are given this function xs, then we can find xt. So the inverse Fourier transform of the for the function xs is written as xt, where xt is the Fourier inverse of xs, which is equal to 1 by 2 pi integral minus infinity to infinity xs e raised to power iota st ds. So these two functions xt and xs, okay, in the time domain and in the frequency domain, they together form a Fourier pair. Okay, and the coefficient of this integral is 1, and the coefficient of this inverse integral is 1 by 2 pi. Okay, so you can also take here 1 by 2 pi in the first integral and 1 in the second integral. So what we mean to say that the product of the coefficients of these two integrals should be 1 by 2 pi. So you can also take 1 by root 2 pi here and 1 by root 2 pi here. Okay, so in different books you may find different notations. The only thing is that the product of coefficient of this integral and coefficient of this integral, the product should be 1 by 2 pi. Okay, so this is one result. Also in Fourier series we have seen that we can find Fourier series in terms of cosine and sine functions. So similarly in Fourier transform we can find Fourier transform, cosine transform and sine transform, depending upon if you are given a even function or odd function. Okay, so if the function xt is even, then the Fourier cosine transform pair is written as this. Okay, so the Fourier cosine transform of xt, which is denoting here by x of cs, means cosine transform of xt, and it is integral 0 to infinity xt cos st dt. Okay, and its inverse transform, that means the Fourier cosine inverse transform of xcs will be xt function back, which is 2 by pi integral 0 to infinity xcs cos st ds. Okay, and because the function is even, okay, so this function will give 2 times 0 to infinity. Okay, and this function will also become 2 times 0 to infinity when instead of exponential you have a cos, and xt is even, then this whole product will be even. So integral minus infinity to infinity will be actually 2 times 0 to infinity. Okay, and here also it will be 2 times 0 to infinity, so it will be 2 here and 1 by pi here. Okay, so basically the product is 2 by pi. Okay, so instead of writing 2 here and 1 by pi here, we are writing 1 here and 2 by pi here. Okay, just for the sake that we are treating 1 as a coefficient in the forward transformation, and whatever coefficient is there in the reverse transformation. Okay, similarly, if the function is odd function, then the Fourier sine transform pair is written as this. Okay, the Fourier sine transform of xt is integral 0 to infinity xt sine st dt. Okay, so that's a forward Fourier sine transform, and its inverse Fourier transform is 2 by pi 0 to infinity integral of xss sine of st ds. Okay, so we can calculate Fourier transform, and if function is even and odd, we can also calculate Fourier cosine transform or Fourier sine transform. So let us take say one example and see how to calculate the Fourier transform of a function. So obtain the Fourier transform for the function ft is equal to 1 minus t square if modulus of t is less than 1 and 0 if modulus of t is greater than 1. Okay, so there is a inverted parabola between minus 1 and 1, and outside this the function value is 0. Okay, so minus infinity to minus 1 function is 0, then from minus 1 to 1 there is inverted parabola 1 minus t square, and then from 1 to infinity again value is 0 from here. Okay, so we want to find the Fourier transform of this function. Okay, so by definition the Fourier transform of a function is integral minus infinity to infinity ft e raised to power minus iota st dt, and this we write as a function fs. And because the function is given this, so from minus infinity to infinity we can break it into minus infinity to minus 1, then minus 1 to 1, and 1 to infinity into sum of three integrals. And the function is only non-zero in this minus 1 to 1 integral, so this integral can be written as integral minus 1 to 1 where function value is 1 minus t square, this exponential dt, and the other two sum of integrals will be 0. So we can solve this. Okay, by integration by parts. The first function is 1 minus t square and second function is exponential. So first function into integral of second function, which is e raised to power minus iota st by minus iota s, then the derivative. Okay, so minus sign and derivative of this, which is minus 2t, and integral of this exponential, so which is e raised to power minus iota st, divided by minus iota s. There is already 1, so it becomes minus of s square. Then sign changes to plus, derivative of this function, which is minus 2, and integral of this function, which is again an exponential, divided by minus is, which multiplied with this becomes is cube. Okay, then the next will be a negative sign and derivative of this, which is 0. Okay, so further terms will be 0 if we do the integration by parts. Okay, the limits are minus 1 to 1, so we substitute upper limit and minus lower limit. So at 1 this first function is 0, and at minus 1 also this 1 minus t square is 0. So this first term will be 0 at both limits, and these two will give value on substitution upper limit minus lower limit. Okay, so we can substitute and we can write that this is the Fourier transform of the function ft. Okay, so we can plot it, this fs function, in the frequency domain, and so this is the Fourier transform of this inverted parabola. Okay, so this is how you calculate the Fourier transform for the function. Okay, and the transform may not actually always give a function in real, it can be complex. Okay, so I just give you one example of that too. So say obtain the Fourier transform for the function ft where function is t in 0 to 1 and 0 otherwise. So given this function, minus infinity to 0 it is 0, and from 1 to infinity it is 0. Only between 0 and 1 function value is t. Okay, so to find the Fourier transform, again we use the definition that Fourier transform of function is integral minus infinity to infinity ft e raised to power minus iota st dt, and function value is t in 0 to 1, so this integral can be divided into three parts, and we can represent it as 0 to 1 function value st e raised to power minus iota st dt, other integrals will be 0. And so we can integrate this by parts. First function t, second function exponential, Then a negative sign, derivative of t is 1 and exponential integral is exponential by minus s square. Lower limit 0, upper 1. So substitute upper limit minus lower limit. So once we substitute limits, we get this function as the Fourier transform function. It's a complex function. Okay. So we are not going to plot this. You can, if you require, you can plot this by separating the real and imaginary part. So we'll require two plots to plot this function. Okay, in complex plane. Okay, so we know that if you are given a complex function, that we need a z plane and uv plane. So similarly for this, okay, one can plot using two planes. Okay. So now I just add some of the important properties of Fourier transform which can be utilized, okay, to find the Fourier transform of some more complex functions together with the definition. So if the Fourier transform of function xt is written as x of s, then the first property is linearity, that the Fourier transform of sum of functions is sum of their individual Fourier transform. Okay, so Fourier transform of a times x1 function plus b times x2 function is equal to a times Fourier transform of x1 plus b times Fourier transform of x2. Okay, so that's linearity. Okay. The second property is scaling or change of scale, that if Fourier transform of xt is xs, then the if we change the scale of t to at, okay, then the Fourier transform of x of at is 1 by modulus a x of s by a. Okay, so that's second property. And I'm not giving proof to this because we have already proved such similar properties in Fourier series. So similarly you can prove them. Write the start with the left hand side, write the Fourier transform of this function as the integral, separate the integrals and write the back the right hand side. Okay, try to formulate the right hand side. So third property is the shifting property. Okay, so again, if the Fourier transform of xt is xs, then the Fourier transform of shift function x of t minus a is e raised to power minus iota as x of s. Okay, so that's just like in Fourier series we have first shift theorems. Okay, so similarly shifting property in Fourier transform. Okay. The fourth property is the Fourier transform of derivatives of function. So Fourier transform of first derivative of x with t is iota s xs, and in general for Fourier transform of nth derivative of the function, if Fourier transform of function is known, then the Fourier transform of nth derivative of function is iota s power n xs. Okay, the fifth property is the modulation. Okay, that the Fourier transform of xt is xs, then the Fourier transform of xt multiplied with the cosine function cos of at is half of x of s minus a plus x of s plus a. Okay, so this is something new which was not defined in Fourier series, so I'm giving a proof of this. Okay, the Fourier transform of the left hand side. Okay, by definition Fourier transform of any function is a integral minus infinity to infinity of that function multiplied by exponential e raised to power minus iota st integrated with t. Okay, and because the cosine function can be written in terms of exponential sum, so cos of at we can write it as e raised to power iota at plus e raised to power minus iota at by 2. So we just convert this into exponential. We can multiply these exponentials and combine them, and rewrite this integral as sum of two integrals. Okay, by linearity. So it can be written as first integral with this exponential combined as e raised to power iota a minus st, and these two exponential combined in the second integral e raised to power minus iota a plus st. Okay, now if you look at this integral, then it is nothing but the Fourier transform of x with s replaced with s plus a, so that's x of s plus a. And similarly this is a Fourier transform of x with x replaced with s minus a, because we need to take a minus sign outside to write this exponential in negative, e raised to a minus I s minus at. Okay, let's say x of s minus a. So modulation theorem says that the Fourier transform of xt is xs, then Fourier transform of xt times cos at is half of xs minus a plus xs plus a. Okay, so if you know the Fourier transform of any function, then immediately you can write the Fourier transform of a function multiplied with a cosine function. Okay. Okay, so now I define this property here, which is convolution property for the Fourier transform. And for that, first we define what is the convolution of two functions. So the convolution of two functions in time is gt convolution ht is integral minus infinity to infinity g to ht minus tau d tau. Okay, so this is the definition. So if we take the Fourier transform of convolution of function, then the Fourier transform of convolution of g and h is equal to the product of their Fourier transforms. Okay, so here product is a convolution product, but here it is a simple product. Okay, so the Fourier transform of convolution of two functions is product of their individual Fourier transforms, and Fourier transform of gt we can write it as gs, and Fourier transform of ht is hs. So immediately we can also write an inverse formula that Fourier inverse of product of two functions is the convolution of the inverse functions. Okay, so I'll just give a proof of this result, that the Fourier transform of convolution of two functions is the product of their individual Fourier transforms. Okay, so start with the left hand side, that the Fourier transform of convolution of two functions, and by definition convolution is this integral, so we can substitute that it is a Fourier transform of this integral. And by definition of Fourier transform of any function is a integral minus infinity to infinity of that function, which is this function, times exponential e raised to power minus ist dt. Okay, now we can change the order of integration. Okay, so here integration is with tau first and t second, so we can change the order and write dt first and d2 second. Okay, limits are minus infinity to infinity for both, so it's the complete plane in t tau. So we can change the order of integration and write dt first and d2 second without affecting the limits. Okay, limits remain same, and this function inside remains there. Now we substitute this t minus tau as a new variable. Okay, say u, then dt times d tau can be written as du times d tau multiplied with the modulus of Jacobian, and you can calculate the Jacobian. Okay, in this case Jacobian is 1. Okay, so the if you substitute t minus tau as u, then g tau remains as it is. This becomes h of u. T is substituted as u plus tau. Okay, t is u plus tau, and e raised to power minus iota is u plus tau it becomes. Then Jacobian determinant, and Jacobian determinant is 1 in this case. Okay, and dt d tau becomes du d tau. Okay, so you just need to go back to the calculus class to see how to substitute the values in double integral. Okay, and then we can rewrite this exponential separating u and tau variable. So these two integrals can be written as product of integral of tau and integral of u, and the first integral is the Fourier transform of g function, and second is the Fourier transform of h function. So immediately we have this result, that the Fourier transform of convolution of two functions is product of Fourier transform of first function into Fourier transform of second function. So this is the convolution property of Fourier transform, and from the inverse immediately we can write that the Fourier inverse of product of two functions is the convolution of individual Fourier inverse. Okay, so this property is very important in Fourier transform. It will be utilized a lot. Okay, together with this property I also provide you some important transformations in a table. See The first one, you are given a graph and the corresponding function for this graph, and then the Fourier transform of this function. Okay, so first is the pulse function, where a single pulse is now of amplitude a, and the time duration is minus t by 2 to t by 2, so that's t time. And the corresponding function for this is that xt takes value a in minus t by 2 to t by 2 and 0 otherwise. Okay, so the Fourier transform of this function is the sinc function. Okay, so it is a t times sinc function of s t by 2 pi. Okay, so that's first result. Second is the Gaussian curve. Okay, which in time domain is written as this, and the Fourier transform of the Gaussian function is again a Gaussian function. Okay, so e raised to power minus t square. Okay, Gaussian, so it is again in the Fourier, after taking transform, it is e raised to power minus s square. Okay, so Gaussian function is transformed to Gaussian function. Okay, uh, third is a impulse function at a. Okay, so there is a impulse at t is equal to a. Okay, in mathematically it is delta of t minus a, and the Fourier transform of a impulse function, if a is positive, is the right decaying exponential e raised to power minus iota as. Okay, so this impulse function, the Fourier transform is e raised to power minus ias. The fourth is a constant function of amplitude a. Okay, value a. So we can write xt is equal to a, where a is a constant, and the Fourier transform of this function is a impulse function at origin. Okay, so there is an impulse at s0. Okay, immediately you can see from here that if a is 0, then the impulse at origin transforms to, if a is 0, is 1. Okay, so impulse at origin gives a constant Fourier transform. Okay, so reverse is expected. The Fourier transform of a constant is a impulse, okay, at origin. Then a unit step function. Okay, so there is a unit step at origin. Okay, written mathematically as ut, and the Fourier transform of this is 1 by is plus pi delta s, where delta s is impulse at origin. Okay, there is a cosine wave. Okay, so written as cos of 2 pi at. Okay, so is a function for cosine, and the Fourier transform of this is sum of two impulses. Okay, so it is pi times impulse at 2 pi a plus impulse at minus 2 pi a. Okay, then there is a sine function, and written as sine of 2 pi at, and the Fourier transform of sine function is pi by I impulse at 2 pi a minus impulse at minus 2 pi a. Okay, and one more I'm giving here is two-sided decaying exponential. Okay, so which is e raised to power minus of modulus at, and the Fourier transform of this two-sided decaying exponential function is uh, 2 times modulus a over a square plus a square. Okay, so you can remember these transforms, which are quite simple, and then you can utilize them to solve many complex problems. Okay, now to add uh, application of Fourier transform, major role is to solve differential equations, either ordinary or partial. So I'm giving you two examples here, one to solve an ordinary differential equation and other to solve a partial differential equation. So let us first take a second order differential equation. D2y by dx square minus a square y is equal to minus some function of x. Okay, gx. So to solve a differential equation which is ordinary, then the method is that you transform this differential equation to an algebraic equation by taking a Fourier transform of this differential equation. Okay, so first step is that you take the Fourier transform of this, then calculate the dependent variable and then take an inverse Fourier transform. This process is very similar to what we do in Laplace. We take the Laplace transform, then solve the algebraic equation, and then take inverse Laplace transform. Okay, so here also, okay, so you need to define what is the Fourier. Y is the dependent variable, so what will be the Fourier of y? Okay, because y is unknown, so we can define that, say the Fourier transform of y function is, say, y of s function. Okay, so the x domain is converted into s domain. Okay, and so because right hand side is also there is a function, so you can say that the Fourier transform of gx is a gs function, and then there is a derivative term, so we also need to use the property of Fourier of derivatives. Okay, so we know that Fourier of another derivative of function is is power n y of s. Okay, so here it is only second derivative, so we only need to write n is equal to 2, so it will be is power 2, that means minus s square ys. Okay, so take the Fourier transform on both sides of this equation with respect to x. Okay, so this second derivative by this derivative property will become minus s square ys minus a square, a is a constant, and Fourier transform of y is ys. Okay, so we are taking Fourier transform on left hand side and also on the right hand side, and on the left hand side it is Fourier transform of sum, and so by linearity we can separate, and then we can use the derivative and this rule. Okay, and the Fourier transform of gx is gs. Okay, so this is an algebraic equation in ys. Okay, so immediately you can recognize that the Fourier transform converts an ODE into an algebraic equation. Okay, so we can solve this equation to calculate this ys function. Okay, so solving for ys, we will get that ys is gs divided by s square plus a square. Okay, and once we have ys, then we can apply and calculate using inverse Fourier transform, because the Fourier of yx is ys, so Fourier inverse of ys must be yx. Okay, so this rule, because of this assumption. Okay, so Fourier inverse of ys will be yx, so apply Fourier inverse transform on both sides. Okay, so yx will be Fourier inverse of ys, that means Fourier inverse of this right hand side, and right hand side is a product of two functions, and we know the Fourier inverse of product of two functions by convolution theorem. Okay, so convolution theorem says that Fourier inverse of product of two functions g and h is the convolution of the Fourier inverse of individual functions. Okay, so that means this can be written as Fourier inverse of one function convolution with the Fourier inverse of second function. Okay, so convolution of Fourier inverse of product of individual functions. And for the first function, if I divide and multiply with mod a, then we know the Fourier inverse of this function, and Fourier inverse of gs is gx, because Fourier of gx is gs. Okay, so for the first function, its Fourier inverse is a two-sided decaying exponential. We already defined this. Okay, and the Fourier inverse of gs is gx, so their convolution. Okay, so their convolution by definition is a integral. Okay, so it is integral minus infinity to infinity e raised to power minus a t minus tau g tau d. Okay, so if you know this gx function, you can substitute the value here and solve this integral. That will be the yx, which is the solution of this differential equation. Okay, so method is simple, that you take Fourier transform, solve for ys, and then you take inverse transform, use some of the properties of Fourier and its inverse, okay, to find a solution. Okay, let us also give one example on how to solve a partial differential equation using a Fourier transform. Okay, so say consider this boundary value problem, which is a heat equation in one dimension. Okay, with the initial condition at time 0, the heat is given f of x by this function. Okay, so say you are given a thin rod with temperature u defined. Okay, so this equation will be satisfied. Okay, and so if we need to find the solution of this equation under this boundary condition, initial condition, and given this bounded function, so by using Fourier transform we can do this. Okay, so first thing to note here is that u is the dependent variable and t and x are two independent variables in this partial differential equation. Okay, so if you are going to take a Fourier transform, then you must specify that with which variable you are going to take the Fourier transform. You are taking the Fourier transform with respect to t or with respect to x. Okay, and U is the unknown, so just like previous, we can assume that the Fourier transform of U is uh, the another function, okay, and U is a function of both these variable x and t, okay. So let us first define this, that the Fourier transform of U x t is UST, okay. By saying this, we mean that we are taking the Fourier transform of this function with respect to x, okay. The variable x is transformed to variable s, okay. T remains t, okay. So the Fourier transform I am defining here is a transform with respect to a variable x, okay. And immediately when t is 0, you can see that Fourier transform of ux0 will be u of s0, okay. So that's the condition given, ux0. So Fourier transform of this condition is us0, okay. And then because there is a, we are going to take the Fourier transform with respect to x, so there is a second derivative term with respect to x. So Fourier transform of this second derivative will be by derivative property this is square ust, okay. So x is transformed to s variable, okay. So okay, take the Fourier transform on both sides of the differential equation, this differential equation, and with respect to x, okay, not with respect to t. So t remains as it is. So take the Fourier transform of the differential equation with respect to x on both sides, okay. So Fourier transform of derivative of u with t is derivative of Fourier transform of u, and Fourier transform of u is u of st, okay. So it becomes derivative of ust with dt, okay. So and on the right hand side there is a constant kappa, and Fourier transform of second derivative by this property, okay, because the derivative is with respect to x and we are taking the transform with respect to x, so it will be minus s square us, okay. So minus s square us, okay. So what we see is that the Fourier transform converts the partial differential equation into an ordinary differential equation. Now the derivative is only with respect to t, okay. So we can solve this ordinary differential equation by the standard methods, and here you can see that the variable separable is there. You can take u to one side and take t to other side, and then integrate both sides to find that if u is divided, then it's du by u, okay. So integral will be log of u is equal to minus kappa s squared dt, so minus kappa s squared t plus a constant of integration, okay. So you can calculate ust by integrating, which is equal to c times e raised to power minus kappa s square t, where c is the constant of integration, okay. And uh, so we can calculate this constant using this condition, okay. And then we can also take the inverse transform, because u is calculated, so its inverse transform is uxt, okay. So we can also take inverse transform. Just to add, if I put t0 here, then it will be us0, and exponential will become 1. So we have that constant c is u value at s0, and u value of s0 is Fourier of ux0, okay. So using the boundary condition at t0, we find that when t is 0, c is us0, and us0 is a Fourier transform of ux0, and ux0 is given fx, okay. So Fourier of fx. So constant is nothing but the Fourier of the boundary condition, okay. Also initial condition given at time 0, okay. So we can substitute this c value back here to write that u function is a Fourier of fx time e raised to power minus kappa s square t, okay. And then to find the this temperature distribution, the temperature u for this road, okay, we take the Fourier inverse transform, okay. So Fourier of u is us, then inverse Fourier of capital U will be small uxt, okay. And on the right hand side again it's a product of functions, so we can apply that it is a Fourier inverse of product of two functions, so convolution is applicable, okay. So Fourier inverse of two functions is convolution of Fourier inverse of individual, so that we can apply on the right hand side, okay. So if I take the Fourier inverse on both sides, then ust becomes uxt, and Fourier inverse of product of this will be Fourier inverse of first, and Fourier inverse of Fourier of fx becomes fx itself, and convolution to Fourier inverse of exponential, okay, function. And this exponential function is with s square, so it's basically a Gaussian function, okay. And we know the Fourier inverse of a Gaussian function. Remember, we are not doing anything with t variable, okay. Fourier transform x converted to s, so inverse transform is on s, okay, and not on t, okay. So it's a Gaussian function in s, and its inverse transform, we know the Fourier transform of Gaussian is Gaussian. Okay, so if I have to take the Fourier inverse of right hand side, it will be this left hand side term in the bracket. So you can compare these two and see what is the value of sigma square by 2 is kappa t. So we can put sigma square as 2 kappa t to find what is the inverse function. Okay, so you can substitute and write that the Fourier inverse of this Gaussian is this Gaussian function. Okay, so it's a convolution of these two functions, and by definition convolution is the integral. Okay, minus infinity to infinity first function and shifted second function. Okay, so x minus w, okay, square, integral with dw. Okay, so if you are given an exact condition fx value, you can substitute and integrate and find the temperature distribution of this uh, heat equation. Okay, so this is how we can solve partial differential equations or ordinary differential equations using the Fourier transform method. Okay, so this is all for today. Thank you for watching, and it needs a lot of practice if you want to do Fourier transform, to try a number of problems and keep learning. Okay, have a good day.